Okay. Hello everyone, my name is Brett Neener. Welcome to ENSC3014. So you're all here for that unit, right? Good. All right, so I'm just going to run through a few things, a few facts about the unit. I guess the thing that you're most interested in is the assessment. How do I complete this unit? So in terms of the assessment, there are three forms of assessment. There are laboratories which are compulsory, and you can select your laboratory groups, and you will need to write a report, and the collection of all of the laboratory reports amount to 25% of this unit. Then you will be allocated to a group for the practicals, which are on Wednesday mornings. You cannot change your group. The selection is deliberate to mix people up in gender and local international students and so on, to build up an exchange of ideas and cultures and so on. So yes, you can change your laboratory group for if you have a need to, but you cannot change your Wednesday morning practical group. If you wish, if you have some cause that causes you problems, then you need to go to student services and demonstrate that there are factors that require you to change your group. But other than applying for it, you need to stay in that group. So there will be 3 group assignments. You'll be allocated a group of about 5 or 6 people, and you work together as a team, and you will produce a report as a team, and you will be assessed in your performance in the team as well as the report. And then there is the final exam. The final exam consists of 2 parts. There is a mid-semester exam, which is worth 25%, and then there's the final exam, which is worth 25%. So the final exam consists of 2 parts. Part A is given at mid-semester, Part B given at the end of the semester. The reason for giving you a mid-semester exam is to try and give you some feedback and to reduce the amount of stuff that you need to remember if we just had all of the exam at the end of semester. So the mid-semester exam will be on the material given in the first half of the unit. Okay, any questions on the assessment? Yes? They will be assigned this week, and they will start next week. Next Wednesday you'll be given the assignment to start with. There is a peer facilitator, somebody who's done this unit a few years ago, is currently doing a PhD, and he is available Monday afternoons, I believe. You should take advantage of go to that group if you can, and ask questions about the unit, about the exercises and so on. So he's sort of free. It's probably more comfortable for you to talk to him than me, perhaps. So that's why we have what's called a peer facilitator. But you can contact me, and my contact details are given here. So I'm in the building behind this building, on the first floor. The consulting hour is Thursday 1 to 2. Feel free to come and see me. All right, now this unit is considered to be very challenging. This unit is not difficult, but it is challenging. It's challenging because it has a lot of material that you haven't seen before. And it's not the sort of unit that you can cram at the end of the semester and magically pass the exam. You will not pass the exam if that's what you try to do. This unit needs to be done on a regular basis. Keep up with the material every week, because each week is not isolated. One week depends on the next. So if you get behind, you'll find it very difficult to catch up. And there is quite a lot of material involved in the unit. But the unit itself, I don't think, is difficult. The stuff in the unit is not difficult. The way we present this unit is mostly through lectures. There are many exercises for you to do, and the solutions are there, and I'd strongly recommend that you attempt the exercises. And please don't look at the solution unless it's a last desperate effort. So quite often you'll find it difficult to do a particular exercise, and you think, oh, let's have a look at the answer. But then if you do that, there's not much learning that goes on. So you need to have a look at the exercise. If you can't do it, then you need to go to the notes or a textbook and try and work out how to solve the problem. Looking at the solution, yes, you'll understand the solution, but if it comes up in exam, you may not necessarily understand it, be able to reproduce it, because it hasn't become part of you. By actually doing the exercise yourself, it becomes part of you. You've got some learning, and you'll find that you'll find the rest of the unit relatively easy, and the exam should be relatively easy. The exam is based mostly on these exercises. So if you can do all of the exercises, you'll do pretty well in the exam. If you want to get a very high mark in the exam, there is usually a challenging question that really tests your understanding of the unit. So that's really just to separate out the people who should be getting HDs, people who really have grasped the content of this unit. Okay, any other questions so far? Nope. Okay, now the way this LMS is broken up is there's unit content, and there is weekly content, and this is week 1, and week 1 we'll be looking at classic conductivity, mostly in metals, because we need to do some quantum mechanics to look at semiconductors. But before we do that, we will be looking at an introduction, some by way of motivation, why you should study this unit and why semiconductors are important. So, okay, so, well, I think probably the reason you've chosen this, well, maybe you haven't chosen yet, this stream of engineering, electrical electronic engineering, is because you understand that electronics plays a role in everything in your life. There's probably very little in your life that is not impacted by electronics. Your health, hospitals, your car, your house, your computer, your banking, just about everything is done and involves electronics. And the building block to all of this electronics is basically sand, silicon, a semiconductor. So the foundation of most of this electronics is semiconductors. So semiconductor conductors actually enable just about every form of electronics that exists. And so as an engineer, as an electrical electronic engineer, you need to understand what semiconductors are, how they behave, how to choose them, what their properties are, and what their advantages are and what their defects are. So let's just have a look at a breakdown of where electronics ends up. This is produced by the US Semiconductor Industry Association. It's from 2015, so it's a little bit out of date. So in 2014, the total global semiconductor market was $336 billion. They're US dollars. What do you think it is now in 2000, let's say 2018? Has it gone down or up? 400 million, very close. $480 million, yeah. $billion, yeah. So it's a huge industry. So in terms of the breakdown, you can see that about 10% goes to automotive technology, so you control systems on your engine and the communication around your car. Communication technology is part of your mobile phone, of course, but digital servers and that sort of thing. PCs, about a third of the market. Consumer products, so smart toasters, smart house, all that sort of stuff. And industrial stuff, which is sort of defense technology and so on. So again, these figures are a little bit out of date. This is, again, 2015, but I just looked up the 2018 figures. So in terms of logic, in 2014, the market was 92 billion, and in 2018 it's $109 billion. So it's still going up. Analog circuits, you think, well, okay, digital, everything's digital these days, but analog circuits are still playing a role. So in 2014, analog circuits are about 44 billion. In 2018, it's 59 billion, so they're still going up. Discrete devices, 2014 with 20 billion. So what is a discrete device? So you know what an integrated circuit is. It's like this chip in your computer, right? A discrete device is an individual transistor. So the market for individual transistors was $20 billion in 2014, and it's now $75.5 billion. So it's gone up by a factor of 4. So discrete devices haven't disappeared. Can anybody guess why discrete devices have increased so much? You would think with all the integration where you can have billions of transistors on a chip, why would you need discrete devices? Prototyping. Most prototyping is done these days is done by software. So you do it all. So the Intel prototyping is all done in-house, secret. Nobody gets in there. Only 4 people in the world can do it. That sort of thing, right? So, yeah. So in the last decade, one of the biggest revolutions has been power electronics. And what's driving power electronics? Solar cells, renewable energies, wind generation. being able to convert the power you get from solar cells into power that you can use to run your house, right? So this is where most of these discrete devices are going. Let's have a look at something else here, might be of interest. Memory. So memories was 79 billion in 2014, 2018. It's $158 billion. So memories are improving significantly. When I was using a computer, if you had 5 kilobytes of memory, you had lots and lots of memory. 5 kilobytes of memory was a box this size, made up of magnetic cores, hand sewn by ladies in a factory. Now you can get a terabyte in something this big. Yeah? So that revolution is incredible, and it's allowing us to do amazing things. Okay, let's move on from this. We've pretty much touched on this already. There's an interesting website or Wikipedia on the semiconductor industry you might want to look at. It goes through and shows the countries that are producing the technology. It talks about the revenue, see 480 billion in 2018. It shows some of the memory distributions. You might want to look at that, and we'll come back to this part a little bit later. Let's get back to my PowerPoint. So, semiconductors. You've probably heard of a number of these semiconductors, some you haven't heard of. So in this unit we'll be looking at mostly these elemental semiconductors, silicon. We won't be looking at germanium very much, although germanium was perhaps the first transistor was demonstrated in germanium. But silicon dominates the world pretty much in the semiconductor industry. Your Intel chips made from silicon mostly. But for very boutique applications, you can use some of these other semiconductors. Applications where silicon really can't work, and there are actually very few places it can't work. One area it can't work is in optoelectronics. You can't make a laser using silicon, but you can make it out of gallium arsenide. So that's one area where silicon is not really cost effective. Even high-speed silicon devices can get very high speed these days, but one of the market areas was gallium arsenide and gallium nitride. Of course, you're all familiar with that, the recent Nobel Prize for the blue LED. So gallium nitride is sort of a semiconductor semi-insulator. It has a very wide bandgap, so we'll learn what that means later on. Zinc oxide was considered to be pretty much an insulator, but people are making zinc oxide semiconductor devices. They're even making semiconductor devices out of diamond. And diamond is probably one of the most, it's probably the best insulator that you can get. So this area between a conductor, a semiconductor, and an insulator, it's getting pretty blurred these days. And then you have esoteric materials like mercury cadmium telluride, which has a very narrow band gap and is used for infrared cameras, espionage, defense, that sort of stuff. And you've probably heard terms about, bandied about amorphous semiconductor, polycrystalline, crystalline. So we'll learn what those things mean in this unit. I'll skip this. So in 1961, Bob Noyce came up with this idea of, instead of making individual discrete devices and connecting them by wires, he said, why not just grow all these things on a single piece of silicon? And that was the invention of the integrated circuit. So this is the patent on the left. Your left-hand side is the patent, which was awarded, and actually Noyce got the Nobel Prize for this idea. what was the big advantage of making devices on a chip? Why do you think it revolutionized the industry? Yes, that's one reason, but at that time that wasn't really the driver. These devices are the same size as you would make as discrete, yes?
Mass production.
Mass production, yes, right? Yes, actually mass production, yes. Hmm? Power efficiency. No, actually power efficiency is a problem, because one of the problems of having so many transistors on a chip is trying to get the power out. So if you pull your computer apart, you'll see that you've got these heat sinks on it and these fans on it. You hear them going when you're driving your computer too hard. So integration is actually a problem.
Do you allow for specialization, different applications?
Yeah, but you can do that in discrete, right, I think. Right? So when they first built the first computer, the ENIAC, and we had valves in those days, right? We didn't have transistors. And they were all wired. You have cables. You open up the back of the ENIAC, and there were just hundreds and hundreds of cables going everywhere. But the good thing was valves, you could see the light on, and if the light was off, you know, the valve was no good, just like the globe. When it went black, you know that it was no good anymore, so you popped out and put a new one in. Transistors, you can't really do that, but one of the reasons that the ENIAC didn't work very well was because of the cables would break and disconnect, and you try and work your way through. So this system was unreliable because people actually had to make the connections. If you do it on an integrated circuit, it's permanent. And there's no way it's going to break. And you can control the whole thing. So that was one of the revolutions that made integrated circuits so important. Yes, scale is very important and so on, but reliability was one of the major reasons for the integrated circuit taking off. All right, so this is all sort of old news to you guys. So there's nearly 1 billion devices for a 45 nanometer CPU. So this has got 4 cores, cache memory, and so on. What does 45 nanometers mean here? It's the gate length, yeah? So each transistor is basically a MOSFET, so we'll learn what a MOSFET is, a metal oxide semiconductor field effect transistor, so we'll learn about transistors. But really the size of that transistor is determined by the gate. So the technology is called 45 nanometer technology. So the smaller you can make the gate length, then the higher the density of transistors you can put on the chip. So the smaller the gate length, the more transistors. So in this case, 45 nanometers, we can stick nearly 1 billion transistors. This is a progression of the gate length starting in 1971. The gate length was 10 micrometers, 74, 6 micrometers, 3 micrometers, blah, blah. So we get down to 600 nanometers in 1990. 600 nanometers is the wavelength of visible light, close to it, right? And so all this technology was done using lithographic techniques, using light to make the shapes, using masks and so on. But now you see, as we progress from 1990, 1999, the length is 180 nanometers. It's now no longer visible, so we can't use visible masks. So 180 nanometers is ultraviolet light. So then we use ultraviolet technology to make smaller chips. Then we get into 2007, which was the 45 nanometer technology we saw in the Intel chip. 45 nanometers. What light is that? X-ray. X-rays, right? So now we're using high energy particles, high energy sources to do this technology. 2014 was a big breakthrough because it's 14 nanometers. 14 nanometers, now it's starting to get close to the wavelength of electrons. And so in order to make these masks, we use electron beams to make the small technology. So in 2018 we're down to 7 nanometers. And this year 5 nanometers. And the prediction is in 2021 3 nanometers, 2024 2 nanometers. Now, you'll learn in this unit that most of your ideas on how conductivity occurs depends on the path length that electron can travel before it collides with the lattice. This length is much shorter than the usual collision or path length that an electron can travel without interfering with the lattice. So this means that this technology, to understand this technology, we can't use the methods we have been using in standard semiconductor technology because they rely on this interaction with the lattice. The randomization that the lattice gives us, we use that to understand how the device works. So these devices are what we call ballistic devices. So you shoot an electron across the transistor and it travels across to the other side. And nothing gets in the way. And so now the technology and the way these things work is totally different. So now we're in a realm, in a world that we have to really change our view of how these things function. We will not get to that sort of understanding in this unit. If you go on to your the master's level in the 5th year, there is a unit that will tell you about ballistic conduction. So this trend, you've probably heard of Moore's law, and so what's been happening is every decade we're getting a logarithmic change in the density of these devices. So when we start off in 1971, this Moore's law just keeps going and going and going. So what does that really mean? This technology, let's say that we were, instead of talking about transistors, let's try and get an idea of what this sort of rapid development means. So if we convert it into populations of people. So in 1971, when the Intel 4004 came out, that's equivalent to stacking people into a music hall, about 2,000 odd people. In the mid-80s, it's like stacking people into a football stadium. In the 2000s, it's like a population of the city I came home from last night, Tokyo. 32 million people. And I can tell you, if you try and get a train in there, you'll understand what density means in terms of people. And then in 2011, we're already talking about the population of China, which is 1.3 billion people. So in terms, that's an incredible change in technology. Let's look at the automotive industry. So if we do the same sort of transition in the car engine in 1970, if we go into the 2000s, your car would have the same power as a jetliner. If we talk about a light globe, to follow the same law, it would be in 20 years, you'd have enough to light up a whole football stadium. So it's an incredible technology. And it's a technology that, okay, yes, we've talked about the size of these devices, but it's not just the size, you have to be smart. And so there's all sorts of weird geometries that were invented to try and get faster and higher densities and so on and so on. So we have nano wires these days. We break away from having two-dimensional devices to three-dimensional devices. We go away to nano wires, and now there are nano dots. So we're changing 3 dimensions, 2 dimensions, 1 dimension, 0 dimensions. Right? So it's an interesting technology. I won't labour on that anymore. You can look at this stuff on the web. Again, the same with this. So this is just showing you all the spots where the technology can help solve problems, and I won't go on that. You're all now familiar with the smart house, so that's really driving an industry as well. Hospitals, of course, these days you go into a hospital, you're surrounded by electronics. And smart civil engineering, bridges are getting wired now. Buildings are getting wired so that you can see if they're going to, for maintenance programs, or if there's any stress that's being caused, so you can monitor these things in the past. Internet of Things, blah, 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 and the ultimate. This is where you start to get problems where we start putting chips into dogs and people and stuff like that. So yeah, it's a technology that is all pervasive, and the whole thing is really supported by semiconductors. So hopefully from that you'll get some motivation for investing some time into understanding this unit. So what we're going to do now is that's not what I want. All right, now this is the notes, so we're going to go on to a bit of dry material now. We've had a bit of a relaxing time talking about the introduction. So can you guys read this at the back? No? Okay. Can you hear me from the back? Yeah? Okay, good. All right, so we're going to have to abandon this and do something like this. Get rid of this. And this. All right. So can you read that at the back? Yep. All right. So the main topic of this unit is semiconductors and transistors. So I just said semiconductors here, but first we understand semiconductors, then we say, okay, what can you do with semiconductors? And then we'll look at diodes and transistors, right? So conduction in semiconductors is a little bit different from conduction in metals, but in order to understand semiconductor conduction and devices, we'll first look at metals, which are a little bit easier, and we can avoid getting involved with quantum mechanics. We will need to get into some quantum mechanics a little bit later, but the quantum mechanics we will be doing is not the stuff probably some of you have done in physics. It's not the sort of high-level stuff. Very basic stuff, just to give you a flavor and an understanding of some of the concepts in semiconductors. Okay, so you've all used Ohm's law, yeah? All the way back to high school, I imagine. You've been exposed to Ohm's law, and when you're solving your circuit equations with resistors and so on, you use Ohm's law to see the relationship between voltage and current. But have you ever wondered why this law exists? What causes this law to come about in a particular material? So that's what we're going to be doing in this sort of what's called classic conductivity. So we will be looking at how electrons, the model we have of electrons moving in a metal. Now this model is wrong, but it works. Right? And we know it's wrong because it doesn't take into account any quantum mechanical effects, but it describes a lot of behavior in metals, so it's still useful. So Ohm's law is this. It basically says that the ratio of voltage to current is a constant and does not depend on the magnitude of the voltage or the magnitude of the current, but the ratio of these two. Right? So the current and voltage are linear related, and we use Ohm's law. Now, in the semiconductor industry, we don't use voltage and current and resistance because these things depend on size, and as you know, size is something we want to reduce, but we don't want it to come into our equations necessarily because we want to be able to scale things. So we will scale voltage in terms of what's called the electric field intensity. So we scale voltage by a length and get something called the electric field intensity, and we'll scale the current by the area, and we'll get something called the current density. And if we take the ratio of those two, it's a constant, but now this is a constant for the material and does not depend on the size of the material. So the resistance, as you know, depends on the cross-sectional area and the length and the type of material you use. If we use these scaled parameters, then it's purely a material constant. And this constant is called the resistivity. And if you play around with the algebra, you'll see that resistivity can be related through the resistance using this equation. So this resistivity is a constant, as I said, is a material constant. And let's have a look at some values. So we know that silver is a pretty good conductor, so we expect it to have low resistance, therefore low resistivity, yeah? And so the resistance or resistivity of silver is 10 to the minus 8 ohm meters. So resistivity is measured in ohm meters, 10 to the minus 8. So if we go to germanium, which was an early semiconductor, the resistivity is 1 ohm meter. If we go to silicon, it's 100 ohm meters. And if we go to water, it's 10,000 ohm meters. It's pure water. If we go to zinc oxide, which is really an insulator, it's 10 to the 8. We go to the crystal salt, so this is a crystal of salt. We try and measure the resistivity of that, it's 10 to the 11. We go to sapphire, which is an insulator, 10 to the 14. We go to the diamond, it's 10 to the 16. So this resistivity, this material property expands 24 orders of magnitude, which is a huge variation, right, of values. Okay, so we are often interested also in conductivity, how much this material conducts, and so that's the inverse of the resistivity. And so we can write Ohm's law now in this way, but what we want to do is work out why we have Ohm's law. Why does it exist for metals? And we're going to use a very primitive model, and this is a cartoon of this model. So we have the red, I should try and get rid of the stuff on the right hand side, I'm not sure how to do that, but anyway. So the red things are the positive ions in the metal, and they are locked in the metal and they don't move. So they're fixed and they're big and heavy. And then you have these blue things spinning around, and these are the electrons, and they're light and they can move and they're fast. And so
strawberry.
So if you watch any particular one, it moves along, travels before it hits something. When it hits something, it changes its direction. It also loses speed. So all of these things are traveling at different speeds. You might notice they're traveling at random directions, and you see that the density of these things is not a constant. If you look at any particular location, the number in a particular area, changes, right? So this whole thing is varying, and so we talk about these electrons as if they're a gas in a container that you might have studied in high school, Boyle's law and so on, where you stick a gas, you change the pressure, volume and so on, and you'll see the speed change and all that sort of stuff. So let's get rid of this before. So this model considers electrons to be a gas. So these particles are moving around, they collide with each other, they collide with the lattice, and when they collide, then they change their direction. Now these things carry charge, the electrons carry negative charge, the metal ions that form the metal are positively charged. So if you try and measure the voltage across a metal, a conductor, what voltage do you get? Zero. Yeah. There's no voltage across a conductor. Actually, that's not true. Because if you remember this cartoon, you have this fixed positive lattice, positive charge, and then you've got all these electrons moving along. And if I take a line at any one time, I don't get cancellation completely. So actually there is a voltage across a conductor. But on average, that voltage is zero. Yeah? So on average it's zero. So this fact that there is a voltage, and you can measure, if you get a chance, you get a resistor and put an oscilloscope probe across it, you will see these fine lines moving around zero. And that's the noise, what we call noise, thermal noise, and that's because of this random movement of these electrons. So on average, there is no voltage. Now this is an important point. The number of electrons and the number of positive charges is equal. And so on average, there is no charge anywhere. Charge balance. Yeah? If you try to disturb this charge balance by moving the electrons away in a particular area, there is an incredible force that will bring them back. So the force of nature, if you like, in this material is one that always tries to maintain neutrality in the material. So this concept of charge neutrality in the conductor is critical. Right? It's a very powerful force. If the charge balance gets disturbed, there's an incredible force that will bring it back. Okay, so these electrons are moving around, they're all traveling in different directions, they're all traveling at different velocities, and so they have kinetic energy, and the average kinetic energy is given by this term here, where Kb is Boltzmann's constant, T is the temperature in Kelvin. So this says to me that if I try to heat this conductor up, then the average velocity of these electrons increases, yeah? It's the same as your gas in a container. You heat the gas up, they move faster in the container. This is the similarity with the gas, yeah? So this law here, this average kinetic energy, is the same law that you would use for a gas. So the average or thermal velocity of these electrons is given by this term here. And so the question then is, one question I'd like you to think about is, okay, if I was to talk about a free electron, then you'd know what mass I want to use, but I've got an electron inside a material. Do I use the same mass? And the answer is no. So the mass of the electron changes in the material, but it doesn't change because of relativistic effects. It changes because of the influence of the lattice. And so we'll understand that a bit later, but that requires quantum mechanics, so we won't go to that. So this law also says that if I go down to 0 Kelvin, all of these electrons, what happens? They freeze out, yeah? Stop moving. And we know that's not true. Right? So again, quantum mechanics tells us that these electrons will never sit still. They'll always have a certain amount of energy. But this gas law, I mean, it's surprisingly effective. So what is the speed of these things? What is the average thermal velocity? At 300 Kelvin, it's 400,000 kilometers per hour. So these electrons are moving around in the metal at 400,000 kilometers an hour. Is that relativistic? No, it's a long way from relativistic, so we don't need to consider relativistic effects, but it's pretty damn fast, yeah? Okay, so in a vacuum, if I have these electrons at 300 Kelvin, there is no lattice and there's hardly anything in the space except a few electrons, then in 1 millisecond this electron will travel on average 100 meters. Yeah? Inside a conductor this can't happen because it'll run into the lattice, and so the time between collisions is likely to be less than a millisecond. And so actually they don't get that far. And so there's a randomization, but there is an average, what we call an average free path length, that they will travel before they collide. So this is one concept you need to understand, mean free path, and then we also understand that there is a certain mean free time between collisions. Okay, I think this is probably a good place to stop. Before you go, these lectures are recorded. It is helpful to come along to the lectures to listen and then go home and use the recordings to reinforce what you heard. By all means, ask me questions or ask the peer facilitator questions, but please regularly study this unit. Do not leave it until the last few weeks of semester. Okay, I'll see you on Wednesday.